So we're delighted today to be joined by Professor Ralph Schönrich, who's coming to us from University College London. Ralph was originally a student at LMU Munich, followed by a Hubble Fellowship at Ohio State, and then a senior research position at Oxford alongside an ERF. Ralph is an expert on dynamics, particularly chemodynamics of galaxies, including the Milky Way. He's also one of the people very heavily responsible for understanding the local standard of rest of the sun. He looks very sprightly, but this is actually Ralph's fourth hour of lecturing this morning, even though it's only 11 a.m., so he's well warmed up for us.
Did you bring the ice bucket?
And I can't see the title on the screen, so I can't exactly remember what he's going to talk about, but I know it's going to be fantastic, so please welcome Ralph Schönrich.
I'm the jet-lagged one. I should fail the memory test. I shortened the title because it was too long. I mean, you see it on the invitation. I'm very sorry about being a little bit wacky wonky now because I got up at 4:30 this morning and then had to lecture because I got my lecture schedules at UCL wrong and so somehow bilocated myself transatlantic. Anyway, so in case I fall asleep, please wake me up, please shout loudly. What we are going to talk about today is basically something where there was also some creaking and cracking at different corners of astrophysics. And that was basically one of the signs of it is always when different people measure something and they agree with each other, but only in small groups. And the small groups really get into troubles with each other. So this is basically for the past 30 years, unless you read Johnson 1957, but for the past 30 years, we've known that we live in a barred galaxy, something that looks basically much like that. So you have this rotating galactic bar in the center. I don't know how many dynamicists are here, but it's basically one of the central instabilities in a galaxy. Your center collapses into a bar. Just think about it if you have an axisymmetric disk and you just put all stars, which you can do easily onto the same angle, then you get a bar, and that is, of course, favored in free energy. And so this bar rotates at the center at a certain pattern speed. I'll talk more about it, but typically, it rotates a little bit slower than the surroundings so that the corotation radius at which the stars go around the galaxy the same speed is somewhere out here. And in our case, the sun would be somewhere here. Oh, sorry, somewhere here. The bar has just passed us, and we would be looking at the bar from a sharp angle, which reaches about halfway our distance to the galactic center. Okay, now big question in astrophysics is how fast does that thing rotate? And basically, depending on whom you ask, you got different answers. And I'll talk more about this, but you see there's basically a factor 2 between measurements, and each measurement has a small error bar. So something is very wrong, and we'll shed a bit light on why that went wrong. Now, I, of course, also Googled what you get when you talk about slowing bars. And that was a bit depressing. I think we shouldn't go into that too much, but it basically gives you all the topics that I would like not to talk about today, and then basically what we are getting in the evening. But then if you enter galaxy-sized disks, not that one, you actually get to the right story. So what this talk is going to be about is that we actually managed to measure for the first time that the bar in the center of our galaxy decelerates. And I'll show you a bit more what that actually means for us. First of all, credits. There's 2 people behind that work. My 2 students, both brilliant. If you can hire them, I congratulate you. One is Jennifer Friske. She came on actually a summer project. And then within a summer project, learned how to integrate orbits, do full simulations, and actually found out by examining the Gaia data that the only way how you can cope with this is actually when you do a slowing bar. And then similarly, she had to go back and do her bachelor's thesis. while writing a major paper. She managed that. And then Rimpe Chiba was my PhD student. And we had a completely different project and decided that we don't do what we announced to the funding agency and just do something completely else. And I mean, ex post, when I apologized 3 years later, they said they were fine with it. So all is good. Anyway, so he did a lot of very, very nice theory. He explained the whole thing. So a lot of what you see is actually Rimpe's work. And Rimpe is currently at Toronto. Jenny is now my PhD student. But if you want to hire her, I think she is entering the job market next year. And a lot what Rimpe did, you'll see in this lecture. I took out the technical parts because I heard there's a lot of non-dynamicists here. So I won't bother you too much with the equations. And I trust that those who are really worried about them got them last week when Rimpe actually was here giving a talk at IAS. Okay, now all this touches upon a fundamental question: is how do we actually measure dark matter, right? And probably everybody of you knows, so I can go through that. Basically, there's 4 major ways how we do it. One is, of course, galaxy clusters. That was the first word Zwicky claimed that you need dark matter to explain the gas being held together in the centers of galaxies. You have, of course, the motions in galactic disk. Albert Bosmer's thesis should be mentioned there as one of the foremost works. Babbage did it actually in 1932, but didn't have conclusive evidence, just rotation curves are flat. So you need dark matter to explain that. We have merging dwarf galaxy streams, basically everything that flies in the halo that tells you that some dark mass must be there. And of course, the large scale structure of the universe, and I won't go much into that. There is a problem though, which is after discovering that this dark matter is there, people went and asked, what is it? And basically, anything goes, right? And I just throw up a few topics. And this is by no means exhaustive. And I'm sure there's some particle physicists who are very insulted that I didn't put up their favorite model for dark matter. And the reason for this is a bit in the nature of the measurement. I mean, there is also some stuff where we try to fix dark matter. And one thing that I would mention, which we can talk about also slightly in a discussion, is if you look at galaxies, there are cores in galaxies. So the dark matter halo doesn't peak. It basically has a hole in the center. And when you do that, people were claiming warm dark matter as the reason, or fuzzy dark matter, or basically anything with low mass and maybe some interactions or not. But I would claim that you don't need warm dark matter because the bar will do that for you. It's coarset, and we'll see a bit how that is done. Now, why do we have so many different possibilities? Basically anything goes, including errors in gravitation. Then particle experiments, you know the story, you can put more and more of these up. They are all brilliant, but they don't yield anything currently. And so the frustrating question is, why don't we know more, and can we maybe do something about that? And yeah, you can do a bit if you think about why that is. Because all those methods that you have up there have one thing in common. It's very different things you go on, but each of these methods does the same thing. It maps the gravitational potential or force, looks for the unexplained force or gravitational potential, and then ascribes it to dark matter or some issues with modified gravity. Okay, good. We can do that differently now. I just mentioned for completeness, because people sometimes throw the bullet cluster up. It's a very nice piece of evidence. But again, the modified gravity people, I don't want to go into those arguments, but it's a peer-reviewed paper. Those people here claim that it's a proof of dark matter. Those people here claim that it's a proof for modified gravity on the same data and citing. You can do it unambiguously. And this is actually, if you look back into our history, why are we not basically living on trees in physics anymore? The reason for that is that we found systems that repeat, a frictionless system that repeats its motion over and over and over and over. That's how we got away from Aristotelian physics, right? That thing that everything wants to come to rest and then friction dominates everything. People looked into the sky, saw celestial mechanics, and they actually managed to discover modern gravity and physics. Now, the point is, when you look at those galaxies, this is also your one-time events. You see a once snapshot of a galaxy, a one snapshot of a satellite flying through. There's not much turns you get on the whole thing. Whereas if you have something that turns over and over many times, it becomes a precision measurement of something. In the case of the solar system of gravity. And another analogy to the solar system, of course, we can't do that in the galaxy because galactic stars need 250 million years to go around, and we currently have nothing that really measures this. But we can do something else. That touches what is with the modified gravity. Now, if you look into the solar system, there is the Greek and Trojan asteroids. That's those little dots that rotate here. So basically around Jupiter at a 60-degree angle on each side, you have asteroids that are caught in the corotation resonance, right? They rotate around at the same velocity as Jupiter. You also see them spinning backwards. In addition, you have higher resonances. That's the 3-2 resonance, if I'm not mistaken. And so asteroids can remain on those resonances and remain caught. Now, the only trick is to find the analogon in the galaxy, right? Which one is that? Well, it is, if you want to measure the spin of the bar, if you know where the resonance is, you know how the bar spins. And you can find the Trojans and Greeks of the bar, which are just, in this case, you take the major axis of the bar, and then basically in the case of Jupiter, Jupiter sits here, out there, and then you have 60-degree angles due to the symmetry here. The Lagrange points are now at 90 degrees to the bar major axis. So if the bar is here, then the Lagrange point will sit somewhere out there and rotate around. And you just need to find the stars that are captured onto the corotation resonance. Then you get a high precision measurement of where the bar pattern speed is. That was, yes, the lower half is just mirrored. So it's boring, so we left it out. But yeah, there's just the same corotation resonance on the other side. Turns out though, because the galaxy is so big and we sit out here, we only see one of the two. Okay, very good. Now, how do you do that? And basically, this is the situation. Rimpe showed that galaxy, we found it a while ago. In all honesty, there's a bit of a conflict. Leo thinks that this is not corotation resonances, but I'm very sure. So in truth, the galaxy looks like that. If you deproject it a bit, it looks like this. The sun is probably somewhere around here. The thing is rotating around that. This is not really like the Milky Way, just to show you the situation. You have the bar there. You have a nuclear disk that has inflows driven by the bar. And then here, this is probably what the corotation resonances look like. So you have the Lagrange points, and bars can cycle, stars can cycle on orbits around those Lagrange points. All happy. Now, how can we see these Lagrange points? Well, this is motions in the solar neighborhood. This is stars moving in the azimuthal direction versus the in-plane motion just quite near the sun measured with Gaia here. And you see there is intense substructure in this plot. And not all of the substructure is the bar, but the biggest features you can guess will be, and you can already see there's something there. This is the Hercules stream. And you can already see a couple of the problems with this. This is not a simple stream. It has those two lobes. Interestingly, it has some substructure and, well, it's very massive, and that's a problem that I'll show you later. Basically, this edge here that is close to the sun more or less corresponds to the edge that you have here in velocity space there. So this is basically the point of the long axis, and this is the stuff going around the Lagrange point here on the bar, if you identify the resonance that way.
Practice.
Sorry?
How far, what volume of space is included here?
Only a point somewhere very close to the sun, about 200 parsec of the sun. You would see the same feature basically anywhere in the data, but of course it shifts depending on where you go in the sample. Now, the problem that I already point out is this is too dense versus this is much, much sparser. So basically, you should have the same density up here. You have the same density here and there. That's just stars moving inwards versus stars moving outwards. The symmetry would normally not break, but down here, you have a factor 2, 3 more stars here than you have on this side. And this is one of the major things that you need to explain. And I'll show you first why the corotation resonance can't really do that, which is if you do the modeling of this, basically, in a normal model, the corotation resonance doesn't show a much higher density. So you can produce the feature down here. You see this being sheared off in the model. So this would be the equivalence of Hercules, but it's too symmetric. This is from Otwin Gerhardt's group in 2017. This is too symmetric, and it doesn't have this overdensity on the left here in the model that is in the data. And that's a major problem. They did this with a constantly rotating bar, and it doesn't work. You get the general feature right, but the density is no chance. The other thing is the Hercules stream has a much higher metallicity. And to go back a step, while we think about this, I would also like to point out another issue. This is the length of the bar versus slowdown, and you might have heard about this a lot. People have been trying to go at the slowdown of bars, and they basically try to do that by measuring the pattern speed of the bar versus the length of the bar that you see in data. And there was a widespread claim basically based on this paper by De Battista and Selwood in 1997 that when you do this, basically the more halo you have there, the slower your bar becomes, and the more slowdown you get, the slower the bar becomes versus its own length. So the corotation radius was claimed to basically detach from the bar if the bar slows enough. However, what we find in data is that bars are typically quite fast. So this is this ratio. No bar can be above 1 or below 1 in this ratio. So that is corotation radius by bar length. Everything above there, don't believe. It's physically impossible. I would actually claim everything above 1. Below 1.3 or so is a problem. And then the data basically lie quite up here at that line, whereas cosmological simulations lie down here. So the argument now is that the bar slows down because it loses angular momentum to the dark halo. And due to that slope down, the bar ratio in curly R should rise in the simulations. However, I disagree very much with that statement because we don't see that in our simulations. We have no idea what they do wrong there, but there's a major part of the community currently claiming that lambda CDM must be wrong because cosmological simulations are down here and the data are up there. And this is the wrong way to argue because this slows down, and I'll show you that the Milky Way slows down and is perfectly up here. So data show you that the cosmological simulations are ruled out, but it's the simulations and not the dark matter picture, actually. The opposition part is, of course, that you say the bar slows down. If you want to keep R high, don't slow your bar down. So you just remove the dark matter and go for modified gravity, but that doesn't work. Counterpoint, there were simulations already by Liath and Asula in 2013. If the bar slows down, this ratio of R virtually doesn't rise over time. And there's other impact factors that determine that. Anyway, back to our problem. Now, we had basically the first signs that we can see the Milky Way bar slowing down in a paper in 2015, where we set up a simulation and the bar slowed down. And I don't go further into this, but basically you see fast stars along the bar. The only explanation is that they have been captured by the bar during growth. Growth means that the bar is slowing, the resonance is expanding, and so you see fast stars here. But in this simulation, you see the typical picture where the bar slows. The bar slows with bumps in the pattern speed. These are interesting. I'll talk about that later. And in the same simulation, the bar length grows. Now, back to our problem with the pattern speed. Let's try to really understand this. Why is this conflict between the different measurements? The conflict was between not what Hercules is. Everybody says Hercules is linked to the bar resonant structure. But in one case, in the original picture, Denen basically said that Hercules is actually caused by the outer Lindblad resonance of the bar. So when the stars do one more epicycle per bar passage, versus stars that are sheared off below the resonance. And the counter picture with this is the fast bars. And in the data, you see that nicely. The counter picture is that you have a slow bar where the corotation is out here. So this would be outer Lindblad. Here it's corotation, but then you have this symmetry issue. And I show that the right one is right. So what are those resonances? Basically, you just make a combination of your orbits. You have the pattern speed of the bar, the phi pattern speed, so the where you go around the galaxy of your orbits. And then if you take a multiple of the radial oscillations, that brings your pericenter passage always at a fixed angle of the bar when you're in one of the Lindblad resonances, and here when you're in the corotation resonances. There's a whole forest of minor resonances. They all don't exist. You'll see why. And basically, corotation is here. You can then look where these conditions are matched, and you have outer Lindblad resonance, corotation, and inner Lindblad resonance in this order. Now, basically, what do they look like? This is non-resonant orbits. That's boring. They get a bit elongated here, depending on where you are relative to the resonances. And the resonant orbits are basically when you are on the Lindblad type resonant orbits. Again, here, outer Lindblad, you have the pericenter either on this side or on that side of the bar, always at a fixed angle. So this is in the corotating system of the bar. You plot the orbit. When you come closer to the corotation, you get more pericenter passages in relative to the bar, and then have a forest of resonances where you count up the number of nodes until you reach corotation, where you rotate around that Lagrange point, and then you go in towards the inner Lindblad resonances and the X1 orbits that support the bar. Okay, now that's just the description. We had this here already. One thing that I quickly want to introduce, because I'm talking about it way too much, I'm not going to explain it very much, but actions, you have Scott here. He'll probably have lectured you about that a dozen times already. Basically, you have 3 actions for orbits in a galaxy, and when you take your phase space in a simple problem like the harmonic oscillator, action really just boils down to the integral over the momentum dz. This is when you go round in your phase space. This is your phase space flow here in round circles. Then the area under each of these ellipses, that is the action of an orbit. The great thing about action is A, it describes how large your amplitude is. B, when I slowly make this oscillator more narrow after being wider, the action stays conserved, so you can directly predict that this orbit here transforms into that orbit here. And so in short, the actions usually in an axisymmetric potential, one is the angular momentum, one is the size of epicycles in the plane, and one is the vertical oscillation size. We just look into the plane. And then when you have a resonant system, so first you have your classic actions in this plane, you had circular orbits here. So this is basically LZ goes up here. You only see at this point the zero radial action stars there with that angular momentum, but you see stars visiting from other guiding center radii or other angular momenta at increasingly high actions when you go out there. When you put a resonance there, you can define a similar set of action coordinates, but let's quickly look at how the orbits fly. This is when you have an axisymmetric potential, two stars here. They rest in J phi, and this is the action angle coordinates. Now, once I introduce a resonance, like the corotation resonance that you see here, the bar rotates. The stars, now when you put this potential here, the stars get caught in a resonance, for example, here in the corotation resonance around the Lagrange point. And that means that they acquire new coordinates. So basically in a plane of angular momentum versus the radial action, on the corotation resonance, you dance forth and back on this ladder. In JS, which is just the angular momentum, because you go round this Lagrange point here, you dance around in the angular momentum, reach a maximum when you're further away here, and reach a minimum when you're closer to the center. So in this dance, angular momentum changes. So this was what was originally behind radial migration in stars, and I won't go further into that. But this libration action here, this describes how far you're away from the Lagrange point. So if you're at libration 0, which would be somewhere outside this plot, you're sitting on the Lagrange point, higher libration action, you move up those contours here. That is the orbits that are closer to the separatrix here on the surface of the circulation. So those here have maximum JL, and those have smaller JL closer to the resonance. Okay, now with all those prerequisites, we need another ingredient, and this is annoying. Liouville's theorem, hands up, who knows Liouville's theorem? Who doesn't? Okay, quick explanation. Liouville's theorem, those who don't Liouville's theorem, hands up if you know the collisionless Boltzmann equation. Yes, whoever taught you the CBE without talking about Liouville's did something wrong, because the CBE is Liouville's. And you should prove Liouville's and then go to the CBE. So this is the CBE. Anyway, Liouville's has one single character, and it's so easy. You go into Hamilton formalism, you formulate a time operator, and then do it, and you see that it's contained. What Liouville says is that the phase space density of any patch of phase space moving around in a conservative system is conserved. Or in other words, the phase space volume of any patch of phase space is conserved. It's the same thing to say. This means that whenever you go round in your phase space between space and momentum, you can change the shape of a patch, but you can't change the density of a patch. And that is one important thing to understand here with that bar. It's been used for the phase spirals, we did that. But in the case of the bar, this goes very, very annoying, actually. Why? Because I showed you this corotation picture, and you see that Hercules is vastly overdense, right? And now we get into physics. What happens here is, when I go into the resonance, you saw that the star stands forth and back on this ladder. That's the only thing that happens when you switch on a resonance. Now, when do I see a resonance? I see a resonance when along the separatrix, I get a density contrast between the resonant space and the non-resonant space. Okay? This density contrast I need to get somehow. However, EJ, Jacobi integral, you get that from Noether's theorem, who was here in Princeton, or most forgotten usually, this is very important, is conserved. That means that for the Lindblad resonances and all higher resonances, the rungs along which you go forth and back on a resonance are inclined in JR. At the corotation resonance, they are parallel in JR. However, a galactic density distribution, which I have in this plot now, is largely concentrated towards low JR and falls off to high JR, okay? So what I plot here is just the overdensity and the underdensity when I switch on a resonance. So I go into a smooth space, I switch on the bar potential, and I asked, how does my phase space density change when I just switch on a bar with those resonances? And you see very nicely, this is the one-to-one. This is this outer Lindblad resonance that you've seen. And because stars get moved between those rungs, you exchange phase space up here with phase space down here, or mix phase space up here with phase space down here. The density in this plot falls off slowly to the right because galaxies are concentrated at lower angular momentum. And it falls off quickly to the top. So because you move stars from down here to up here, the density falls in here, and it rises on the outer edge of that outer Lindblad resonance, which means when you have a bar switched on, the outer Lindblad, any higher resonances, will have a large density contrast on their surface, which is what you see on Hercules. So naively, you would say Hercules must be a higher resonance. On the corotation resonance, because JR is conserved, the density contrast is minimal, right? And you need to solve this. Now, if we look into the data, and so this gave rise to radial migration, if we look into the data, we now need to find a better way of identifying the corotation resonances and really fixing what of the two is it really that we see in the galaxy with those two pictures. Jenny discovered those wave patterns. This is just the radial velocity versus angular momentum. We first wanted to look for vertical waves. This was far more impressive. This is no wave. When you plot that against angle in the galaxy, so this is angular momentum, outer disk here, inner disk there. This is when you go around the galaxy, you go around here, you just take a slice, and this is this phi angle difference around the galaxy at the same time. You see that those ridges in U are inclined. And in particular, I point you to this arrowhead shape. That is what tipped us off. You see it here. And this arrowhead shape is again nothing else. So here's the velocity space, here's the action plane, J phi, JR, you see some ridges, that must be some resonances. Good luck identifying those here. It's hopeless. People have done any possible identification. Identifying it here is clear because all those here are inclined. That one here is an arrowhead shape. And that's this lens circulation that you see around the Lagrange point, inner part, outer part of just the Lagrange point circulation of the corotation resonance. So case clear, this is the corotation resonance. Well, you just stick that into your model and just what I said happens when you just switch on your resonances and switch on the bar. This is the U velocity pattern that you get. Shape right, something out here is not really looking right, but this arrowhead is fixed, but it's way too faint due to that density contrast issue.
Loop in the action plot, why don't the
it's what we don't see. The Gaia sample is limited in space. So what you see here, this width down here is just how far you see in space times the radial velocity. So we said here, this is how far we look to both sides at these data. And then this envelope here is stars that reach us from different angular momentum at higher JR. That's the ones in your velocity diagram in the envelope. Okay? Now, to solve this, the only way out, you already saw it, is to go back to the slowing bar. And now the important thing, I already showed a slide like this once before. If you have a slowing bar, you instantly know that you have an inertial mass into the dark halo and not modified gravity. What happens on these resonances is basically if you play the organ and you have a choir, if you slowly ramp up the speed, they can follow. If you ramp the speed up too quickly, they can't, and you lose the resonance. You can go into more depth of that a bit later, but basically what we can now do is, if the bar slows down, the resonance moves outwards. If you do it slow enough, you can just keep the stars that were on the resonance. Liouville dictates that the phase space density is conserved. And now if I move stars from, let's say, 4 kiloparsec to out here, I have a much larger fetch in density, and I can get the density contrast I want. And there's another thing. So when you look at the galaxy, it's dense in here, it's less dense out there, and it's more metal rich in here and less metal rich out there. And we'll come back to that in a second. But when you do that and you ramp up the bar pattern speed, if you slowly slow your bar, basically what happens is when the resonances, so it moves and slows from top to bottom, in your local velocity space, the resonances move up in angular momentum. So you see this resonance here, 1-to-1, then the outer Lindblad moving up through the solar neighborhood near the current pattern speed of the bar. You see the corotation up. And now the resonances are way too strong if you do that. So if you do that slow down too slow, the resonances are too big and they can basically hold everything in their path. If you, however, do a slowing at about 12% per giga-year, reasonably fast, then those resonances take less stars and you get nicely the arrowhead shape, and you also get that jagged terrain and the radial velocity in between. So everything suddenly fits. And so with those data already, you have proof. Basically, the only solution for this is that the bar is slowing. And here you can then make a diagram and ask, what do you get in bar amplitude versus different bar slowing rates? So here the bar slows quickly, here the bar slows slowly, and you just ask, when do you have the right strength of your resonance in the observations to explain the data? You put a plot there, and basically you ask, when do you lose the stars in sufficient number from your potential? I think I'll jump over that because it's a bit boring. And then from that, you can just fix the pattern speed by looking for the right point here. However, when you do that, the right speed, you manage to actually reasonably explain the pattern that you see up here with what you have down there. Velocity is all right. So at this point, we wouldn't have made any press release yet because there's a few steps in between. So you need a second thing that proves that you're right if you make a claim like that. And actually, oh yeah, this is just fixing the pattern speed. The second thing, when you add the slowing bar, is, okay, let's repeat on this again. So when we slow the bar, the resonance moves up here. It can capture stars. And it can capture stars only, by the way, in the case of the corotation resonance, if the resonance is growing in phase space volume, otherwise you violate Liouville. But it takes those stars with it, and then you bring them upwards. And you can also already see that this acts a bit like tree rings. You see that the blue star here, this is far further inside the resonance than the big star, the red star out here that came from further out. I'll show you another simulation in a second. And again, to repeat, denser here, sparser there, that we have already explained. But now we get to something else. We saw before that Hercules is more metal rich. When you do that exercise with more stars here, the resonance is moving out. So this is angular momentum counting down while the resonance moves. The color of the stars indicates from where they come. Red is from inside the galaxy, blue is from the outside of the galaxy. And you see here already very nicely, they are ordered. This is because the process is slow. Adiabaticity means that action is conserved, which means the libration action inside the resonance is conserved. Now the stars remain ordered. Now the resonance grows like tree rings on a tree. Everything that you pack on at the resonance later, modulo diffusion that Chris is treating, will actually be near the surface of the resonance. So you have one clear prediction of this scenario, that you would find a metallicity gradient along the resonance. The galaxy is more metal rich on the inside, and it's less metal rich on the outside. The core parts here of those stars should have higher metallicity inherited than the outer parts. Now, I mean, I already showed you there is a higher metallicity in the center of this resonance. This is what it looks like in the observed plane. You expect that there's more stars from the inside of the galaxy towards stars further from the outside of the galaxy. That inner disk region is basically ramped or pushed by the resonance, dragged by the resonance into this outer disk. Now, let's observe this. We can get this by coloring this in metallicity. You can take isochrone metallicities, color this plane in metallicity, and you already have kind of a win. The Hercules stream, this resonance stuff, is definitely more metal rich here. Now, it's more complicated than this, and that gave us a bit of headache, because you also see out here, this is high JR, this is the outer part, the old part of the disk, and in here you have younger stars. Old stars tend to be metal poor, and so you have, unfortunately, because you're so far out, you have this trend towards old stars overlaying the overall higher metallicity in here. To get a clean measurement, so we had to slice this. So you can first slice this in action. You see again, this is J5 versus JR. The low action stuff is high radial action stuff. Old stuff is up here, lower metallicity. You see the overall metallicity gradient of the galaxy. So outer disk more metal poor, inner disk more metal rich. And you see this pronounced step up near the resonance, and you already see there's something more going on here. So you just need to slice this up along lines of JL. And basically, because while you go down in JL, so towards the center of the resonance, you're being pushed up to higher and higher JR. You basically need to set Humpty Dumpty back together. So you need to slice this up at constant JR, then measure the gradients in each bin of JR, and then put those gradients back together into a common metallicity gradient towards the center to correct for this effect. And this is what you get. This is 50 sigma or so. There's no doubt that you have something. And there's a consistent increase of metallicity of the resonance towards the inside of the resonance. Oh. This is photometric metallicities. Spectroscopic metallicities from Gaia are still a mess. So this is, you restrict yourself to main sequence stars and then measure by position on the main sequence where you are in metallicity. As long as you clear the subgiant branch, you're fine with that. And there is contamination from the binary stars, but we showed that we have, so you can calibrate against well-known targets and it's fine. So the clusters come out right when you do it. And basically, if you change the pattern speed, so if I change the location of this resonance, if I change the pattern speed of the bar, if I make it slower, this moves up. If I make it faster, this moves down. And you just ask what happens to your nice metallicity gradient versus JL. And it completely disappears if you just get the pattern speed slightly wrong. So your Lego bricks fall apart. And when you do that, you actually get a high precision measurement of the pattern speed, which we didn't advertise, but I think that's the most precise measurement there is of it when you take this. The most important part, however, is, of course, this here shows you, in addition to the overdensity I showed you, that the bar has slowed down. The nice thing is, if you measure the gradient compared to the galactic gradient, you know how much it slowed down. So with that, you get 12% slowing per gigayear. Here you get that it's at least 2 gigayears already, and it slowed down more than 25%. Now with Gaia DR3, DR4, we can dig deeper and try to reconstruct that further down. It's also, I mean, we have not explored that, and will be a lot of work. This also gives you a separate history of the galaxy within the resonance. So you get basically 2 different history tracks in your same sample. One that's in the resonance space protected, and one that's outside of the resonance space. Bit like solar system history, right? The asteroids in Jupiter's resonances, they are the former solar system that survived well protected into the resonances. The rest is all gone. And here you could play the same game. I should mention all the issues. Basically, spirals not understood. Where are they? We haven't seen them in those data. This is worrying. The next things, those R dependencies not fully understood. Orbital structure versus slowing, that's also not understood. So there's a lot of things that we need to talk about. Now, since we have a bit of time left, 5 minutes, do you want to talk about the oscillations or do you want to talk nuclear disk? In the more speed. Or do you have questions now? Let's do questions now.
Okay, you made a number of simplifying assumptions.
Yes.
So one is to neglect the self-gravitating response of the disk.
Yes.
Presumably there's some sort of spiral that's launched from the end of the bar, and that will shift phases and things.
Yes.
Another is that Liouville's theorem isn't really obeyed by real stars because they're born. They come into existence out of gas. Gas is dissipative.
Yes. Yes.
Your analysis when you
in this case, the thing with the age difference, it is a real effect. We more or less constrained it with the JR dependence. So we used the JR dependency to actually basically clean out all those pesky age effects. So as long as we have stars present, we are fine. You also need to think about what you say actually helps me, because that means no new stars form on the inside of the resonance in this case, so they can't contaminate me that much. I believe there is star formation and we'll have to deal with it. The point here is we are high enough up in JR with the measurement that we don't see what's just forming. The stars that are just forming inside the resonance wouldn't be in the sample at current stage. It will be a complication later on. Concerning avoiding the Lagrange points, it happens in the galaxy that I showed you, if you believe these are the Lagrange points, and I'm currently begging 5 observers to observe that thing and give me an analysis of if we have the trends we expect and to help understand this. Other galaxies don't show those holes. There is star formation in that region with those complications, but it doesn't affect the current analysis. The stars that you see there clearly have already been quite old when they got picked up by that resonance because they had higher JR dynamically heating law. And then they just get swept along.
You use the distribution of metallicity to actually determine when the bar formed relative to the history of the information?
Yeah. And so, yes, it goes actually easier than this. So the problem actually, if you look at that measurement here, the problem that we have is we scrape the very surface of the resonance. We don't see the core currently. So you can't solve this by a metallicity distribution out here, right? You need to solve it by going down to the Lagrange point. The old stuff of the bar that was originally captured hangs out at the Lagrange point, but that's 6 kiloparsec away from us, and getting precise metallicities down there is a challenge currently. But your point is fully valid. So what you want is a metallicity age distribution of all stars depending on action on the bar, and you get the history of that resonance. And even more so, this is a history that is less contaminated by all those pesky spiral patterns that happen outside that space, unless you get enough mixing, but that's interesting by itself. So examining that thing is key to understanding the history of galactic structure. Hope that helps a bit.
Yeah, so I kind of wonder, can you predict that the metallicity dispersion inside the bar corotation resonance will be very low if you assume there's no new star form and it's like taken? I mean,
we don't have a blackboard, right? Yeah. No, I don't agree.
For its rate is not
Yes.
overall, but for
No, I don't agree with that. And the reason for that is if you look at what you're sweeping up currently and what you're getting originally, the bar, when it forms, the resonance will sweep up anything that is inside the resonant region, all the stars there. And depending on when you form that resonance, there will already have been radial migration into the disk, and there will be a well-established metallicity distribution. So you inherit a wide distribution of different metallicities inside the resonance. You can ask how much different the metallicity distribution is inside the resonance. And yes, I do agree that it should go down a little bit when you go towards the core of the resonance. How much? That'll tell you about galactic structure. On the surface, it doesn't, pardon, on the surface, it doesn't, it shouldn't change too much. The galactic metallicity has been the same for the past 7 gigayears, give or take. Nothing has changed. The only thing is that stars migrate radially. And the stuff that hangs out on your surface of the resonance, these stars here have been caught just 1-2 gigayears ago mostly. So they are free disk stars that now happen to be in this resonance and being carried outwards.
And also, whether you have any comment on the substructures inside the Hercules 3, like for the density substructure.
One possibility is basically this here. So when the bar resonance forms, this is one thing that will give you substructure. When the bar resonance forms, the overdensity will be on the bottom of the resonance. And then you wrap around in the, so this is Rimpey's third paper. When you wrap around inside the resonance, this mixes up into a phase-space spiral, and this spiral will have over and under density space next to each other. And there's two things how you could see that thing, if it still exists. I mean, depends how Chris's diffusion coefficients work out on this thing. Either you wash it out over time, which is well possible, or if you don't wash it out over time, it'll result in overdensities inside the bar that currently are not disentangled in our analysis. The other thing, how you see it, and that was the bumps in pattern speed, because, so this is the torque over time, and because this torque oscillates over time, you see bumps in the pattern speed in simulations. So there might be similar pattern speed oscillations that you can pick up around the disk. But yeah, that's two ideas. For the rest, there's clusters, etc. as well. So I'm not sure. More questions?
Actually, I have another. So, I mean, if we believe your measurement of the bar pattern speed, it's slowing the pattern speed. It's telling us something about the halo.
Yes.
But obviously, but in the absence of a halo, it wouldn't slow.
Yes.
Actually, but a complication is perhaps that there's also some torque on the disk.
Yes.
A shallow vorticity gradient. I would think the disk would tend to accelerate the bar. Do I have the sign right? While the halo tends to slow it, and how does the balance work?
That's a full angular momentum balance that you have to account for. So basically, the bar slows. We know there's a net flow out of angular momentum from the bar. The stellar disk will have two sides of the medal. One is that new disk stars get captured into the X1 orbits of the bar. So you basically fall from 4 kiloparsec onto an orbit that goes past the galactic center, and instantly, give or take, we are currently also trying to figure that orbital change out. You lose already in the capture half your angular momentum on average. So there's a big flow of angular momentum from the stellar disk to the bar, which offsets the angular momentum that you need to expend to make the resonances in the disk buoyant. So the torque will grow on the bar over time. And you see that actually in simulations that the torque grows by Gaspini now. This growing torque is compensated for the stellar disk very well by what you get by capturing new disk stars. For the halo, the balance is different because the halo is further out. So less gets caught into the so-called dark bar. So the dark bar has only 20% of the mass of the stellar bar, or even less. Whereas the dark resonances out there, dark corotation resonances, has roughly the same amount or more in material as you have in the disk stars. So hence, that is why you see that difference between an only disk and a disk with a dark halo. It will largely depend on the halo kinematics. Of course, you need to do the counting. Under which halo scenario do you have how much mass on which resonance? How much does the density of the surrounding phase space go down when you plow through, etc. So this is what we need to do in the future. You can turn this into a high precision measurement of kinematics of dark matter on those resonances. But to do that, the last ingredient, which you should never forget, is the gas in the galaxy. So that's readily quantified. Count your stars, put it into the slowing rate, you get your angular momentum. This is the unknown you can measure by measuring the angular momentum. Also, little comment, moment of inertia of a bar is not trivial, so that needs to be added to this. It's not that you just slow it down, but the shape changes. But the last point, this is something that bugs me much more, is the gas in the disk, because that merely flows inwards and it gives up major amounts of angular momentum. In simulations, you can see that it stops the bar, but I actually have a minute. That one we are in the process of quantifying. If somebody gives people observations, because we have the nuclear disk detected inside the galaxy, and basically, this is the situation that flows down here. And all you need to do is, we modeled this, Jenny was on it to get her hands on this. But basically, right here, basically the inflow, this is an inflow model, but the nuclear disk abundances that you can measure can be in chemical evolution directly connected quantitatively to the loss rate from the disk. So all you need, measure the total mass of the nuclear disk, assess the loss rates in the disk over the history. You have the total mass of material that has flown down the disk. You have that angular momentum part. That one we've solved more or less. The thing why we can't put a number on this is nobody gives you abundances for the nuclear disk currently, because you would need to point Keck at it for a night or so. And they have more important things to do. So that is also an appeal. I mean, we need data of this in the nuclear disk, high resolution abundance data. It's one of the most important things.
Question. Can you go to your ladder plot in J phi and JR?
Yes.
One of the way back.
Okay, this one.
Yeah. Yeah, that's fine. So these resonant structures, pendulum-like libration resonant structures,
Yes.
there's one at every JR, right?
Yeah.
And you're doing this measurement at a fixed JR, but the stars that are at a fixed JR today weren't there yesterday and won't be there tomorrow, because you have this constant flow through JR space.
Yes.
So in fact, you're not really trapped in one resonance, you're trapped inside that resonance, then tomorrow you're trapped in a slightly different resonance, which is in different place in JR space.
Well, it's still the same resonance. I mean, it's
The
the same.
same diffusion.
Right, but you have this two-dimensional slow plane, but this extra dimension in the
Yes.
And so because this is tilted, I could actually get captured into that resonance just by being kicked in JR. At a fixed J phi, I get kicked from outside of the resonance
Yes.
into the resonance.
Although,
And you're implicitly allowing for that because you're saying we have to do this in fixed JR and we have to get rid of the age velocity dispersion relation.
What you say is normal diffusion, and compared to the size of that thing on the speed at which it moves, diffusion is slow in my books. So basically, and also, I mean, never forget the diffusion you're talking about. May I call it diffusion? I mean, we have so many different words for that. But the diffusion you're talking about basically gives you a jitter here around. And this jitter can suddenly get you on resonance and get you out of resonance. But we need to model that. I fully agree with it, and we currently have that in the models. But in the time that you jitter a bit around here, the resonance has moved a huge amount of space here.
Diffusion in that slow space, which would be the horizontal direction here, but it's just the point that it's also in the vertical direction as well.
And you would be fine if your diffusion coefficient is roughly similar, which I assume. So your metallicity gradient, for example, that we looked at would be conserved at the time. But you have three things that blur you around the edges of your separatrix: the inherent pattern speed oscillations, the normal diffusion, and what the spirals patterns and dwarf galaxies do to you. And yeah, valid point. And given the value of what you get out of this, I fully agree. Give me 3 postdocs and I'll do it.
Let's leave it there. The college is going to be in the Dilworth room. Let's thank Ralph one more time.